problem, pure water is used to absorb 87% of sulfur dioxide from a gaseous mixture in a tray column. The water flows from the top of the column at 25 kmol per hour and in contact with the gaseous steam enter at 5.3 kmol per hour, which contains 18 mole% of sulfur dioxide. The equilibrium data for this system is to be represented by an equation of y equal to 4.3x, where y is a mole fraction of SO2 in the gases and x is the mole fraction of sulfur dioxide in the water. Okay, take notes that you need to draw the schematic diagram for the process. So just represent a schematic diagram, label the 4 streams involved. Okay, and then you need to calculate the molar flow rates of the raffinate and extract, which is you need to find the extract, which is Ln, okay, raffinate, which is V1, okay, in kilomole per hour. And then you need to determine the number of theoretical stages for this process. Okay, remember again, when you want to find the theoretical stages required for this process, what do you need? One, you need to have an operating line. Okay. Next is to have the equilibrium line. Okay. Alright. So equilibrium line is given here already, which is equal to y equal to 4.3x, and the operating line is given by the top coordinates and the bottom coordinates given from your solute mole fraction in each stream. Okay, so let's say what we have here. Okay, so you need for operating line you need xan with yan plus 1 and xa0 with ya1. Okay, so you need to connect these two coordinates and form an operating line. For this one, you need to do substitution. Okay, so just briefly look at the approach that you're going to do. Okay, so for this one, you might want to have the value for x and the value of y equal to 4.3x, and then you make substitution for x. Let's say you have 0 here, you get 0 here, and then choose a value for x and then solve for the y. So you get 2 more coordinates for the equilibrium line, then connect the 2 coordinates to form a straight line. Now let's extract the data from the questions. Pure water is used to absorb 87% of sulfur dioxide from gaseous mixture. So in these questions, we are given SO2, which is the solute. Pure water is the solvent. And the removal of the solute in the gaseous mixture is 87%. And then this is a gas mixture, therefore we are going to use solute to represent the symbol for A, solvent with the symbol of C, and then gaseous mixture, so we have a diluent here which also involve symbol B for diluent. And then it is mentioned that the pure water is flow from the top of the column at 25 kmol per hour. So this is the flow rates of the solvent. So these solvents are contacted with the gases, where the gases flow rates is given by 5.3 kmol per hour, and this gas flow rates contains 18 mole% of SO2. So this 5.3 kmol per hour will represent the flow rates of the feed gas. 18 mole% of SO2 represent the mole fraction of sulfur dioxide or the solute in the feed gas. And then the equilibrium data is given by the equation of y equal to 4.3x. And we need to use this information to draw the schematic diagram for this process, to calculate the molar flow rates of the raffinate and extract, and to determine the number of theoretical stages required for this process. Now let's draw the schematic diagram of the gas absorption column. And this gas absorption column is the trade column. We are going to insert the data in the schematic diagram for the easy reference. So we are given the solvent, which is pure water, is used in this question. Pure water means that the X C naught is equal to 1. Therefore, X A naught is equal to 0. And we are also given that the water flows from the top of the column with the flow rates of 25 kilomole per hour. So this is the information where L naught is equal to 25 kilomole per hour. And then we also given that this water is used to absorb 87% of sulfur dioxide from the gases mixture. So we are given the information here, YaN plus 1, okay, which is consists of 18 mole percent of SO2, which is 0.18. Okay, and we know that it is diluted in the other gas. So let's assume we have a diluent. Okay, so the balance will be the diluent, which is now 0.82. Okay, and then we also given that the gases flow rate is 5.3 kilomole. So you are given Vn plus 1 is equal to 5.3 kilomole per hour. Okay. Alright, what else do we have? 25 kilomole done already. And then, okay, so you're given the remover. So you're going to remove, okay, so you're going to remove your solute, okay, so that what you get is only 87% of the SO2 from the original feed gas. So we know that Vn plus 1 consists of the flow rates of A, N plus 1, and Vbn plus 1. Okay, so what it's mentioned here, you're only going to remove 87 out of the original flow rates of the solute. So you're going to extract 87, so you're going to have Ln, which is also consists of LAN plus LCN. Okay, so Ln is equal to LAN plus LCN. So what is mentioned here is LAN that you're going to remove from the feed gas will be recovered at the extract equal to 87% of the original amount, which is VAN plus 1. Okay. And the balance of the solute, okay, which is about 13%, will be released at the raffinate stream. So we can just write here, okay, which is V1 consists of VA1 plus VB1, because V1 is the gas stream. So what it will be released will be in the gas form. So the diluent, okay, which is originally fed from the bottom of the column, okay, will be released at V1 as raffinate. And then we have the solute, which is sulfur dioxide, okay, which is fed in the column, okay, will be removed in the extract, and some will be released to the raffinate. So we can just write something like this, okay. So your VA1 at raffinate stream is equal to 13% out of the original solute at the feed stream. Okay, do not forget that we have pure water feed at the top of the column, and the flow rates is 25 kilomole per hour. We are also given the equilibrium line equation, which is y is equal to 4.3x. So, in order to draw the operating line, we need x a naught. We also need y a1. Okay. We also need y an plus 1. And we need x an. Okay. To solve for x an and y a1, okay, to solve for x an and y a1, which is the solute components at the raffinate and at the extract, we need to solve v an plus 1. Okay, so to solve v an plus 1, because we are already given the information that the mole fraction of the solute is 0.18, okay, 0.18. Therefore, V an plus 1 in the feed stream is given by the mole fraction multiplied by the flow rates, which is Vn plus 1. And we have 0.18 multiplied by 5.3. Okay, so you can get, so what's the answer for this? It is 0.954 kilomole per hour. So now it's easy to calculate, okay, the LAN. So LAN now is given by 0.87 multiplied by 0.954. We get that from the VAN plus 1. So we have, okay, which is equal to 0.83. Okay, 0.83 kilomole per hour. So same thing here, we have VA1 equal to 0.13 multiplied by 0.954, which is equal to 0.124. Okay, so kilomole per hour. Okay, so by knowing that, okay, it's easy for us to calculate the flow rates of diluent in the feed gas. Okay, we would like to now to solve for VBN plus 1. So to calculate VBN plus 1, we just need to have, okay, VBN plus 1 is equal to 0.82 multiplied by 5.3. Okay, 5.3, which is equal to 4.346 kilomole per hour. Okay, now we're going to solve for XAN. Okay, but to solve for XAN, we need to solve for the LN first. Okay, so we know the LAN already, so we need to solve for LCN so that we can find out the total flow rates for the extract. So the LCN is the flow rate of solvent in the extract, but the solvent that you have, which is water, the flow rates from the top of the column is 25 kilomole per hour. So therefore, okay, LCN is given by the same flow rates of water. Okay, so that will give you the total of Ln equal to 25 plus 0.83, okay, which will give you 25.83 kilomole per hour. Okay, so now we can solve for XAN. But what is XAN? XAN is the mole fraction, therefore it is the flow rates of LAN divided by LN. Okay, so LAN is given by 0.83 divided by the total flow rate, which is 25.83. So we get the information. So the mole fraction of solute at the extract is 0.032. Okay. Okay, we solve for XAN here. Okay. But we still need information on YA1. Okay. So what is YA1? YA1, we need to solve for V1. Okay. V1, which is VA1 plus VB1. So you know the VA1 already, which is VA1, which is, okay, 0.124. Therefore, VB1 is all the other components in the feed gas, which is also equal to the VB n plus 1, which is 4.346 kilomole per hour. Okay. Alright, now we don't have much problem to calculate YA1 because YA1 is given by VA1 divided by V1. Okay, and the answer should be 0.124 divided by what? Oh, you need to add everything first. 0.124 plus 4.346. So that will give us the amount which is equal to 4.47. Okay, kilomole per hour. So we need just to divide 4.47 here to give 0.0277. Okay, so now we have YA1 equal to 0.0277. So we have completed the values to represent the coordinates for the operating line. Okay, now let's transfer all the information from the messy schematic diagram to this diagram. Okay, so that it's going to be clearer to see the values of the mole fraction for the solute for every streams involved in this column. Now, let's label the coordinates. Okay, so we have x an with y an plus 1. And from the top of the column, we have x a naught with y a1. Okay, so the next thing is to substitute the value 0 and 0.0277, and the bottom part is 0.032 with 0.18. Okay, so we have a pair of coordinates. Okay, so these coordinates, the bottom value, the bottom fraction of the solute will give us the coordinate for the operating line. Okay, so remember the operating line that we have. So let's sketch here. So the operating line that you have will be something like this. Okay, alright. Okay, so you're going to label this one, okay, and this one as the coordinate. So this coordinate, which is your operating line, the bottom of the line is given by 0 and 0.0277, and the top part is 0.032 with 0.18. Okay, so this is the coordinates that you get from the fraction of the solute in the process. Okay, other than that, you're going to have equilibrium line. Okay, and the equilibrium line looks something maybe like this. Okay, let me draw in the red color. Alright. Okay, and that line represented by y equal to 4.3x. Okay, so you need to know the coordinates that you would like to label for your equilibrium line. Okay, which is, this is equilibrium line. So you can just plot something like this. Okay, so here is the x value. Here is the y equal to 4.3x. Okay, so because we are dealing with a very dilute solute, okay, so you might want to have a coordinates of at x0, y also 0, and maybe you can go, if you look at this part, the x value is 0.032, so you might have a little bit further. Let's say you're going to use 0.05 and calculate the y value. Okay, you might want to have 2 point or 0.215 here. Okay, so enough to have 2 points to get your straight line. Okay, now let's transfer all the information that we have in the graph. Okay, so you need to know how to select your range for the x-axis and the y-axis. So what is the x-axis? Okay, x-axis is the mole fraction of x, which is your liquid, and then the y-axis is the mole fraction of the gas. Okay, alright, so remember, you need to draw two lines. One is operating line and the other one is the equilibrium lines. Okay, if you look at the scale of the y coordinates, the highest you can go is 0.18 for this particular operating line. Okay, and here the range, the highest value of x you can get is 0.032. Okay, so you need to use a proper scales in order to use the whole page of the graph given to you. Okay, so don't draw a very small graph here, okay, because it is not easy to look at, and you're going to have a difficulty on reading the scales. So I suggest if you were to have this kind of values for the y-axis, maybe the highest you can go here is 0.2. Okay, so let's say you pick the highest here is 0.2. Okay, because this is near to 0.2. Okay, and then for the x-axis, the highest value that you can go is, let's say, 0.4, okay, 0.04, because this is maybe approximately reaching 0.04. Okay, so by doing that, you can have the bigger scale here is 0.04 for your graph paper. Okay, so now you're going to label everything, okay, and then plot all the coordinates and form two lines. Okay, the first line comes from the coordinates that you have at the bottom part of the column. The second coordinates come from the top of the column. And for the equilibrium curve, you're going to use equation of the straight line given, which is y equal to 4.3. Okay, 4.3 multiplied by x. Then you do find the substitution for your x in order to find the value for y. Okay. Alright, so this is how the graph looks like. Okay, so when you label, you make sure that you label all the coordinates, you label all the lines properly. Okay, and then the last step that you need to do is to draw the stages involved. Okay, so this, you draw the horizontal line starting from the bottom of your operating line. Okay, which is I draw in a blue line. And then when it touches the equilibrium line, draw the vertical line until it touches the operating line. Then you need to draw a horizontal line until it touches 45-degree line. So you need to complete this, okay? Because when you talk about the limit, so this is the limit for the x value, and that one is the limit for the y value. Okay, so once it is done, draw the number of tray. Okay, so how do you draw? You draw the first steps here, which is number 1. This one is number 2. Okay, so the number of theoretical stages or trays will be equal to 1 and something. It's not more than 2 because your last line intercept at this position, so the steps is not completed. So let's say how to read this. So you read this by labeling. Okay, let's say you label this one is the position of A, this one the position for B, and this one the position for C. Okay, so you might want to calculate the number of boxes, or you might want to measure the length. So it should be the length, which is the length of AB divided by the length of AC. Okay, so this is approximately equal to, okay, 1. According to my graph, I have AB 3 boxes, so 3 over, and overall we have 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say I have 11 here. So the answer should be 3 divided by 11. You get equal to 1.27 3 trays. Okay, so this will be your answer.